video, we will be talking about the Pascal triangle. Now, the Pascal triangle, in my opinion, is one of the most beautiful wonders of mathematics. It's a very simple structure, yet it is a very powerful tool for solving many different types of mathematical problems. Now, if you open the Mathematics Analysis and Approaches guide, you will see that the Pascal triangle appears under 1.9 as part of the binomial theorem. Now, the binomial theorem will be covered in a separate video, and the IB states that you should be able to use the Pascal triangle and that you should be able to find these coefficients, NCR, which we'll explain in this video, using both the formula and technology. And this is what we will be covering today. Only when you truly understand the Pascal triangle and how to compute its coefficient can you then move on to the binomial theorem, which I will be covering in a separate video. Now, the Pascal triangle is a very easy triangle to build. Basically, we start on top with 1, and as we move down to lower rows, we keep adding the two numbers we have in the diagonal. So whenever we don't have a number, it means we have a 0. So here we have 0 plus 1, which gives us 1, 1 plus 0, which gives us 1. And then we move on. 1 plus 0, 1, 1 plus 1, 2, and then 1. 1, 3, 2 plus 1, 3, 1 plus 0, 1. 1, 4, 6, 4, 1. Now I have just filled 2 more rows, and as you can see, it's super simple to keep going. Now before we move on to more theory, I'd like to give you some background information about this triangle. Despite bearing the name of the French mathematician Blaise Pascal, this triangle was actually known to mathematicians centuries before he was born. It appears in the works of Indian mathematicians as early as the 2nd century BC. It was studied by Persian poet and mathematician Omar Khayyam in the 11th century, and it was published by a Chinese mathematician in the 1300s. And that's more than 300 years before Pascal was even born. Pascal's contribution in 1653 was not to discover it, but to study it so deeply and publish so widely that it became forever associated with his name. What makes this triangle truly magical is the extraordinary contrast between how easy it is to build and how breathtakingly powerful it turns out to be. To construct it, you need nothing more than the ability to add two numbers, right? A child could even build it. And yet, hidden inside this childishly simple structure lies some of the most profound mathematics. So this triangle appears across an astonishing range of mathematical disciplines. In algebra, as we will see, it gives us the binomial theorem. In combinatorics, it answers questions about how many ways you can choose R objects from N. In probability theory, it is at the core of the binomial distribution, which is also part of the IB curriculum. It also appears in calculus and in number theory. I invite you to do your own little research about it just to see how powerful it truly is. Now, going back to the triangle, let us introduce some notation. We want to be able to refer to the numbers in this triangle by referring to their position. So which row they belong to and which column. So here when I say column, I'm talking about these diagonal columns. So for the rows, we're going to denote the row number by the letter N. And we're going to start with 0, which is an important thing to remember here. So the first row is actually the row of n equals 0. And then we move on. 1, 2, 3, and so on. For the columns, we're going to do the same thing. And we're going to denote the column by the letter R, starting from 0 again. You can think of this somewhat as like a coordinate system. So instead of having like an x and y value to locate a point, we have an n and r value to locate an element in the triangle. So for example, if we take this number 6, so 6 here has n equals 4 and r equals to 2. So using the n and the r value, we can actually express the elements in the Pascal triangle. And we have two different notations for that. The first notation is by using these long brackets where we put the value of n on top of the value of r. So this is not a division or anything, these are just the two numbers on top of each other. And now the second notation is the one that you will see in the guide, which is NCR. So you put the n value and then the letter C followed by the value of r. Now this can also be read n choose r, which as the HL students will see, this denotes the number of ways you can choose r elements from n. We will cover that in another video related specifically to HL. Now let's use this notation to represent a few numbers. So if I write 5, 5, that means this is the element in the triangle that has n value 5 and r value 5, which is the number 1. Now, if I write 4, 3, then we go to the row n equals 4 and then r equals to 3. So 4, 3 is equal to 4. Now, I invite you to pause the video for a few moments just to find the values of these two expressions. So you can look at the triangle and see which element has n equals 3 and r equals 1, and then which element has n equals 6 and r equals 4. This is a very straightforward process. N equals 3 is here, and then we move on to r equals to 1, so we get 3. In the same way, we go to n equals 6, and we find r equals to 4, which is here. So 6, 4 is equal to 15. Now using this notation, instead of having the Pascal triangle written with the actual values of the elements, we can present it like this. So the triangle we have on the right side here actually have the n and r value that corresponds to each element. So for example, the number 1 that sits at the top of the pyramid here has n equals 0 and r equals 0. So writing it in this form allows us to make some observations about the values of these numbers. So one thing we notice is that the numbers that we have on the diagonals are all equal to 1. And these correspond to the entries where the r is equal to 0, as well as when the r is equal to n. So we can deduce that n0 is always equal to 1, which is also always equal to nn. Now, another thing you might have noticed is that this triangle is actually symmetric. So if we draw a line about the center, you see that whatever we have on the left side is reflected on the right side. And so obviously n0 and nn would have the same value. And that is true for all other elements. So if we take, for example, n equals 6, for r equals 0 and r equals 6, we both have 1s. Now, if we take one step to the left from here, and one step to the right from here, we get the exact same value for 6, 1 and for 6, 5. And that is true for all the rows. 5, 1 is exactly the same as 5, 4. 4, 1 is exactly the same as 4, 3. And that these two values, the second and the before last one, are always equal to exactly n. We can write n1 is equal to n, and so is n minus 1, the number before last. Now, by simply using these two observations, even without drawing the rest of the triangle, if I ask you what is 8, 0, even though we haven't still reached n equals 8 in our triangle, you should know that this is just equal to 1. Similarly, if I tell you what is 12, 1, then again, you remember that n1 is always equal to n, and so 12, 1 is simply equal to 12. If I tell you what is 10, 9, then you should notice that 9 is just before 10, which means this is the before last element in the row, which means it will also be equal to 10, using this rule here. Now, what if I ask you to compute 10, 7? This one doesn't follow any of the rules that we stated above. Does that mean that we have to fill the Pascal triangle up until n equals 10 to find the answer? Of course not. Mathematics wouldn't be as beautiful as it is if this is actually what we had to do. So although the way we get the values of these triangles is by starting from one row and computing the values of the row below using the row above, there is actually a formula that allows us to find these values. And this formula is in fact in your formula booklet. So before I write down the formula, I first want to make sure you understand the factorial notation. So the factorial notation is an exclamation mark. So 3 factorial. This simply means that you start with 3 and you keep multiplying until you get to 1. Similarly, 5 factorial, we start from 5 and we keep going all the way till we reach 1. So as you will see in the formula booklet, the formula actually involves factorial. And before I write it down, I want you to make sure that even if it kind of seems a bit intimidating at first, it is actually a very simple formula to apply. And I will give you a trick to do that. So the formula says NCR, or as we said, NR, is equal to n factorial divided by r factorial times n minus r factorial. So don't be intimidated by what this formula looks like. First, I will apply exactly what the formula says so that you can check for yourself that it does in fact give us the coefficients of the Pascal triangle. But then I will give you a very easy trick that allows you to do it without having to compute the entire formula. So let's take, for example, 5, 2. So what the formula is telling us is that we write the factorial of 5 at the top, and then we divide by the factorial of 2, which is our r value, multiplied by the factorial of 5 minus 2, which is the factorial of 3. Now, the first thing you can observe is that this simplifies with that. So that way we're just actually left with 5 times 4 at the top and 2 times 1 at the bottom. And that, of course, is just equal to 10. So if we go and check in our Pascal triangle for n equals 5 and r equals 2, the value is indeed 10. Now let's try for 6, 4. 6 times 5 all the way until we get to 1. And then we divide by 4 factorial multiplied by 6 minus 4, which is 2 factorial. And again, the 2 factorial at the bottom will simplify with the 2 factorial at the top, and then we can just simplify more. So we are left with 3 times 5, which is equal to 15. We can go to our Pascal triangle and check for n equals 6 and r is equal to 4, we of course get the value of 15. So the trick I was talking to you about relates to that part always simplifying, which is the last part of the denominator simplifying with the last part of the numerator. So instead of actually following the formula step by step, I invite you to do this trick. So always start from the bottom and write the factorial of whatever you have here, which is your r value. So 2 times 1. And then move on to the numerator and start writing the factorial of your n. But the rule is you have to have as many numbers at the top as you have at the bottom. And then you stop. Now let's compute this value. The 4 and the 2 simplify and we get 10. So you see, this is actually exactly the same thing that we did earlier, except we didn't have to write that part of the numerator and denominator that cancel. So again, for 6, 4, always remember you have to start from the bottom. So 4 times 3 times 2 times 1, and then you move on to your numerator and you keep writing the first bit of the factorial until you have as many numbers at the top as you have at the bottom, and you just stop here. And now you can simplify, and we get 3 times 5, which is again 15. So this trick here is very handy because you don't actually have to go through all the steps of the formula. You can just use that method and you get exactly the same result. Now, another reason why this trick is useful is when it comes to expressing something like this, for example. So here, we don't know what the n value is. So using that trick here, very simply, we do the exact same thing. We start from the bottom, 3 times 2 times 1. Now we move to the top. So we start with n, and I want you to think about it for a moment. What should I write next? So what is the term that comes right before n? Here, if we look at 3, the term that comes before it is 2, and then the term that comes before 2 is 1. So here, what is the operation that we need to do for n so that we get the 2 other terms that are right before n? And the answer is simple. We have n minus 1 and then n minus 2. So again, here notice how we have 3 terms at the top and we have 3 terms at the bottom. So in some IB questions, you will have to replace this expression by something like this so that you are able to solve for n. Now, if you want to check that you've truly understood everything I've explained, I invite you to do these practice questions. Pause the video, take your time, and then come back when you've got your answers. I hope you've attempted these exercises. Now let's check the result. So here again, we start 3 times 2 times 1. On the top we have 7 times 6 times 5. We simplify. 6 simplifies with 3 times 2 and we get 7 times 5, 35. Similarly, here we start with the bottom, 4 times 3 times 2 times 1, and then we move to the top, 10 times 9 times 8 times 7, 2 and 4 simplify with 8, 9 simplifies with 3, we get 30 times 7, which is 210. So as you can see here, I always simplify before I go on multiplying. Obviously, when this is a paper 1, you will need to simplify as much as possible so that you don't end up with really big numbers on the numerator and the denominator, and then it's a lot more work to simplify. Now for paper 2, obviously you will have your calculator, which is what we're going to talk about next. How to use your calculator to find the values of these coefficients. Now for the last two, I'll just give you the answer, and I hope this is exactly what you got. So 66 for 12.2 and 126 for 9.5. Now, how do we find these values using our calculator? So in my videos, I'll be mostly giving instructions related to the TI-84, which are generally similar instructions to all the TI models. If you have a Casio or an HP calculator, I invite you to just go on YouTube, and there are plenty of videos that explain how to get these options. So for the TI-84, you need to first press on math, and then you navigate to probability, and then you will find the option NCR. Now the trick here is this. Once you press on that, the calculator has assumed that you've already put an n value. So actually the real order is this. First you put whatever n value you want, and then you follow these steps. You press on math and then prob, and then once you press on NCR, a C will appear here such that you can now put your R value. And then you press enter and you will see that you get exactly the same value as we computed above. So in this video, we have seen how to compute the coefficients of the Pascal triangle using the formula and using the TI-84. As I said, if you're using a different calculator, it's very simple to find the method of computing these coefficients for all the different calculators out there. Now, with this knowledge, you are ready to move on to the binomial theorem, which we will be covering in the next video.